Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
The next speaker is Hari Narayanan, and the talk is entitled Testing the Manifold Hypothesis.
Okay, so, hi, thank you for the invitation to speak here. This is work with Charles Fefferman and Sanjoy Mehta. So, as we all know, nowadays we often encounter data which has many dimensions, and often the dimension is comparable or larger than the number of samples we have that we can analyze. And the analysis of such data is associated with some specific phenomena, one of which is well known. It's called the curse of dimensionality. Among its aspects are the fact that the sample complexity of function approximation grows exponentially in the dimension, and there is also a comparable algorithmic blow up as the dimension grows, which is also exponential. What is also sometimes mentioned is that there are certain blessings associated with data analysis in high dimension, but these are actually not so much blessings as ways of getting around the curse. And also they generally come up mostly in the analysis and not in the actual bounds. So it becomes easier to analyze certain phenomena because of laws of large numbers that comes up in asymptotic analysis. And also there is this phenomenon of concentration of measure, where in high dimensions random quantities start behaving like deterministic quantities. And that is also beneficial when it comes to analysis. So one way of getting around the curse of dimensionality is what is called manifold learning, and this is based on the manifold hypothesis, which is the hypothesis that this high dimensional data actually lies in the vicinity of a low dimensional manifold. And if this were true, we are often able to prove bounds that do not depend on the ambient dimension of the data, but rather on the dimension of this manifold. And this is a hypothesis that has gained a lot of traction over the past 1 or 2 decades. And there is a great deal of work that is based on this hypothesis, where, for example, in isomap, you develop maps that reduce the dimensionality of the data, assuming that it actually comes from some a low dimensional surface embedded in high dimensions. But the question of whether or not data actually lies on a manifold is less well understood, and that is what I would like to talk about today. I would like to come up with a test that tells whether or not high dimensional data lies in the vicinity of a low dimensional manifold. So one comment that should be made when addressing this question is that this is very much dependent on the representation of the data. So there may be representations where data lie on a manifold and representations where they don't. For example, if you have a scene and you move a camera around the scene in a smooth manner, but then you parameterize the image that you see by the position of the camera, that is something that is smooth and it would lie on a manifold. The position and orientation of the camera lies on a manifold. But if the actual scene is cluttered and you try to measure 2 scenes that are shifted by a little bit by, say, something like L2 distance, that is not going to be smooth. So there may be representations where data is on a manifold and other representations where it's not. But here we'll be talking about a fixed representation. And now I'll move on to the statistical and algorithmic aspects of the question of testing if data lie near a manifold. So before I move on, I need to tell you what I mean by a manifold in some quantitative sense, because otherwise, you can always fit a very complicated curve to any number of points. So you have to have certain trade-off between how complicated the curve is and how many points you have and things like that. So because of that, let's introduce a few quantities. So we'll define the reach of a set to be the largest number such that for any r less than that number tau, if you take a point at a distance of tau to the set, so here's the set, then that set has a unique nearest point. In this case, it's this point. So for example, if you have a straight line, then the reach is infinite because any point has a unique nearest point to the line. But if you take a circle of a radius tau, then the reach of the circle is tau itself, because the center point of that because the center of that circle has a unique has several nearest points, and therefore it's not true at tau. So here is a curve of large reach. Basically, the reach is something like this. It's the radius you need to enlarge before which the boundary of that tube starts behaving badly, and that happens at some point like this. And here this has much smaller reach. And we'll define a GE of d, v, and tau to be the family of d-dimensional submanifolds of the unit ball, which have a d-dimensional volume less or equal to v and a reach of less or equal to tau, and a reach that is greater or equal to tau. I'm sorry. So here's our formulation of the question. We are going to assume that data is drawn IID from some unknown probability distribution P supported in the unit ball in a separable Hilbert space, and x1, x2, etc. are these IID samples, and then based on these samples you have to come up with an algorithm that says yes or no, that there is a manifold or there is not a manifold. And so with the error epsilon, given error epsilon, dimension d, volume v, reach tau, and a confidence 1 minus delta, our question is there some algorithm that will take this many IID samples from P and then output yes or no, depending on whether there is a manifold of belonging to this class, namely having bounded volume and reach, such that the average squared error of a random point from this manifold is less than epsilon. So we are asking for a mean squared error to the manifold to be less than epsilon. That's our notion of nearness. So this has two aspects. First, how much data do you need before which you can even answer this question in a statistical sense? Because if you have too little data and ask, does this data lie on a very complicated curve, then just on the basis of that data, you probably would always be able to fit the curve, but it would not tell you anything about the actual probability distribution. And as you got more and more points, your answer would probably come out false. So this is the issue of generalization error, and we have a result which says that the sample complexity depends only on the intrinsic dimension, volume, and reach of the manifolds you are fitting, but not on the ambient dimension of the Hilbert space where the data lies. So that the number of samples you need to answer this question really does not depend on the ambient dimension, and that is good news. And secondly, there is the algorithmic question. So given certain number of data points, how do we test whether or not there is a manifold that lies close to these data points in the average squared sense? And here we are allowing ourselves certain slack. So this is to make the problem easier for us. We allow we don't necessarily say it has to be volume less or equal to v. Any volume less or equal to CV is okay with us. So but it would be nice to make that 1 plus epsilon. Okay, so now I'll talk about the results we have on the sample complexity and then move on to the algorithm. So here's some more notation. Let LMP be the expected squared distance of a random point to M from P, where that random point is drawn from P. And we also define the empirical loss L empirical of M to be the sum over all I equal from 1 to S of the distance of xi to M squared by S. So this is parallel to empirical error and true error. The loss corresponds to true error, empirical loss corresponds to empirical error. And we define the sample complexity to be the smallest number S, such that there exists some rule A which, when given x1, x2 up till xs IID from P, will be able to produce a manifold MA. This is the manifold that the rule produces, whose performance in terms of loss is not much worse than the best possible manifold in the class with high probability. So this is the usual formulation of statistical learning theory. So that's our sample complexity. And it's well known that in order to get upper bounds on the sample complexity, it's good enough to get uniform bounds relating the empirical loss and the true loss. And the reason is that suppose I could guarantee that when I take S samples, the average squared error is over all manifolds. Here are the manifolds on the x-axis, is uniformly close to the true loss. Then instead of optimizing the true loss, which is what I want to do, I could optimize the empirical loss and get an answer that is pretty close, as long if I knew that both of these are uniformly close with high probability. So it's a sufficient condition to get a uniform bound of this kind in order to prove sample complexity bounds. And we are able to prove such uniform bounds over the space of manifolds and show that if S is larger than V times 1 over epsilon plus 1 over tau to the D plus log 1 over delta by epsilon square, then with probability at least 1 minus delta, the loss of every manifold in the class of interest, that is this, is close to the empirical loss with the samples. So this is a uniform bound over the space of manifolds. And the way we prove this bound is by approximating manifolds as point clouds, and then considering a point cloud as the center set of k-means, and then using getting a uniform bound over k-means, which is of independent interest. So the idea is that you have a manifold, but you can actually approximate it as a set of points at a sufficiently small scale, and then view and then declare that the manifold is actually not this manifold, but this discrete set of points, and then talk about the distances to this discrete set of points, but then you are exactly in the setting of k-means. And here, instead of proving a uniform bound over manifolds, you can just as well prove a uniform bound over these point clouds. And this is in fact a stronger statement, because every manifold can be approximated by a point cloud in Hausdorff distance, but the converse is not true. So we are proving a harder uniform bound when one is proving this for k-means. So the question for k-means after a little bit of linear algebra becomes a question of proving a uniform bound over functions of the form minimum over ai dot x, and this is because the function for k-means is minimum over I x minus ai norm square, which is because it's the nearest point square. That's the loss, k-means loss, and you just open it out, get rid of the x square term because that is common, and get rid of the ai term because that is fixed. You get something like this, and this, however, was in high dimensions because we are working in a Hilbert space whose dimension we have no control over. So in order to bring this down to a dimension we have control over, we use the Johnson-Lindenstrauss lemma and randomly project onto log s over epsilon square dimensions. And there, by the Johnson-Lindenstrauss lemma, all the essential geometry characteristics are preserved, and we can do our analysis on this lower dimensional space. And that's essentially how we get a sample complexity bound of order k over epsilon square log square or s over epsilon. And so this is actually the complexity of that function class. It's called the fat shattering dimension, and we can show that this fat shattering dimension is bounded in this way in terms of k and epsilon for k-means, and this leads to a sample complexity that is k over epsilon square some logarithmic terms. So this uses a number of results in empirical processes. Okay, so in k-means there was this lower bound that was known. It was of the form k over epsilon square log 1 over delta by epsilon square due to Bartlett-Linder-Lugosi. What this says is that you really need this many samples before which, if you do k-means on the sample, you can expect to get something meaningful. If you have less than this number of samples, then just doing k-means on that is not going to give you something good in the long run. So this is the lower bound. This upper bound was proven by Maurer-Pontel, which is of the form k square over epsilon square. So this means that k square over epsilon square samples suffice. If you have this many samples and you do k-means on that, you can legitimately expect to get something reasonable. And our bound improves upon this in a reasonable, when k over epsilon is reasonably small because there's a log in front of it. So we get something new for k-means as well. Okay, so now let me quickly move on to the algorithmic part. A consequences of this uniform bound is that instead of fitting to a measure, which is what we were asked to do, fit a probability distribution, fit a manifold to a probability distribution, we can instead just sample that probability distribution and fit a manifold to that because of this uniform bound that we have. So this allows us to do certain dimensional reduction, and you can in fact search for manifolds within the affine span of the samples, and you don't have to search for manifolds in the entire Hilbert space. So this uniform bound leads to a dimensionality reduction of that kind. And so now let me tell you something about the algorithmic question. So here the question is, given n points x1 to xn, is there a manifold with bounded dimension, volume, and reach, such that the average squared distance of a point from that collection to M is less than epsilon? So we have to do an optimization over a space of manifolds given n explicit points. There's no randomness now. So we have a theorem which says that yes, you can do this. It has a exponential dependence on all the parameters of the manifold, but it will output yes if there is a manifold of this class of interest, and it will output no if there is no manifold, not just in the class of interest but in a somewhat larger class of manifolds. And here's the sort of outline of how the manifold goes, how the algorithm goes. So first, you observe that any manifold whose dimension is bounded by d, volume by v, and reach bounded below by tau is almost contained inside an affine subspace of dimension np, where np is some packing number of the manifold. And the reason is you can take a fine net of this manifold, take lots of points in that, and take an affine subspace, take the affine span of those points, and now the manifold will almost lie in that affine span. And this reduces the dimension to np. Now you exhaust. So now we are working in some relatively low dimensional space, and we are going to exhaustively search among all candidate manifolds in some sense. So the space of candidate manifolds, of course, is a continuum. So you can't do that with a computer, but you can look at every manifold in a small part of it, and that's going to be the idea. So you first take an evenly spaced set of points. You're going to have to take lots of these. These are kind of like gross approximations of the manifold we hope to find. Then in the neighborhood of this, you define a vector bundle which for every point in this neighborhood takes an affine subspace of dimension n minus d, where if d is the dimension of the manifold, n is the dimension of the ambient space. These subspaces are meant to be normal to the manifold, so they have complementary dimension, but there is one subspace for every point in this neighborhood. So there are lots of these. This is called a vector bundle over the tubular neighborhood. The base space is this tube, and the fibers are all look like the normal bundle. And then we define a putative manifold as a set of zeros of a specific section of this vector bundle. A section of this vector bundle is a function which for every point assigns a value to the corresponding fiber. So the set of all points which are mapped onto themselves would correspond to the zeros of the section. So this is a specific construction. And then once you have this putative manifold, so this is the putative or the guessed manifold, which is obtained from the zeros of this section. You try to adjust it further in a lateral way to get the actual manifold, and there we are going to do some sort of locally we are going to try to use function approximation, use optimization over functions to get what are called local sections or things that are defined locally on the manifold. And this involves Whitney's inequalities, which I won't go into. And finally, you patch all of these local sections together to get a manifold. So here is one local section, here is another local section. Unfortunately, they don't agree, and that's the whole point. But you take this vector bundle and then you average out using the vector bundle. So you kind of average out and on these, and then you get a global manifold. So that's the algorithm. And some concluding remarks. So we have an algorithm which is more of a theoretical framework for testing the manifold hypothesis, and we have improved sample complexity bounds for k-means. So we would like to make this practical and test on real data, and understand how to make this non-parametric, where you vary the reach and the volume in some intelligent way with data, and how would one improve the efficiency, for example, better optimization over sections of the vector bundle, and how to understand the role of topology in the optimization questions involved. Thank you.
We have time for questions.
So in the definition, you define reach. How is it different from curvature?
So this reach involves global aspects also. So for example, if you took two parallel lines at a distance of r from each other, the reach of that set is r over 2, because there are points at a distance r over 2 that have two nearest points to that set. So it's not just a local character. It measures nearness to self-intersection.
Any other questions? So I had a question actually. So it would be really cool. So I mean, you described, for example, the algorithm finding the manifold, and then if I have some like a classification task or some type of decision theoretic task, and I want to exploit the fact that I assume the data is on the manifold, can I take this approach and couple it with let's say a classification algorithm,
hopefully, yeah,
and then take advantage of that?
Hopefully, yeah. So at the present moment, that that guess manifold, putative manifold, is implicitly defined as something like the set of zeros of a function. So there, in order to actually nail down the manifold, you would need to do something iterative, some optimization to get the manifold. But yeah, I think so. I hope so too. Yeah.
So in the criterion for testing existence of a manifold, you had both reach and epsilon, which is how close points need to be. It seems, at least intuitively, that there'd be a trade-off between the error, the epsilon, and the reach somehow, that you could find. Like if you relax reach, then error could potentially be reduced.
Yeah, that is true, but that trade-off, I think, depends on the ambient dimension. And I don't want to bring in the dimension of the Hilbert space, because actually all of these results work in countable dimension too. So I agree with you, yeah. But if you want to try to fill the space in a Hilbert space, then you really need a lot of volume. Yeah, I agree with you, but the bounds would depend on the ambient dimension, I think, yeah.
Let's thank the speaker. Oh, sorry, one more question.
Just one brief question. Since you have these constants C that enter into the sample size, do you have any idea how big those are? Like if they're 10 to the 30th, it's not practical, but if it's 5, then that's useful.
So those constants depend on the intrinsic dimension of the manifold. And they are exponential in that.
Right, like if you go back to some of the isomap original papers where they were showing those two-dimensional manifolds in free space.
Yeah.
Like, so for d equals 2.
Yeah, I mean, I hope that it won't be too bad. They're explicit. They're not, they're things that you know where they come from. They're not,
Right. So it'd be nice to know how big they were.
Okay, let's thank the speaker one more time.